So let's see what happens when a dipole is placed in a non-uniform electric field. Okay. So let us consider this is the direction of E, and of course increasing rightwards. So we see that non-uniform electric field where the electric field is increasing rightwards. Now let us consider a dipole. So let us consider a dipole. Let this is minus q and this is plus q. This one parallel to, as we see, so here is minus q at A and then plus q at B. Now, what is the force on minus q? This is opposite to E. So, this. And what is force on plus q? This is along E. And as increasing rightwards, so force on plus q in magnitude, this will be more than that force on the minus q charge. Okay? So what we see? Therefore, net force on the dipole, net force on the dipole is along increasing E. So what is the conclusion? A dipole placed in a non-uniform electric field, where the dipole moment is parallel to E, then it experiences a net force along increasing. You understand? S2 if P is anti-parallel to E. Again consider this is increasing as before, but the dipole moment is making 180 degree angle with electric field. So here is minus q and here is plus q, so that the dipole moment P, in this case, obviously in this case, this is the dipole moment. So the dipole moment is opposite to E, anti-parallel to E. Then as electric field is increasing rightwards, so at the position of plus q charge, here electric field is small compared to here, so electric field is smaller. So the plus q charge experiences smaller force. In which direction? Plus q experiences a force along it, but smaller. And minus q, here the field is stronger, and I consider the field is increasing rightwards. So the minus q charge experiences a force larger in magnitude, but the direct side is opposite to it. So this is for F on minus q. So this is F on minus q, and this is F on So the dipole moves physically. So what is this case? So the result is, so what is the result? The net force along decreasing okay, and this is to note that in either cases the torque on the dipole equals 0. Here also torque equals 0. You may recall the formula P is sin theta. So theta is 0, so torque 0, theta 180, also torque 0. But the dipole in such a case experiences a net force. Okay? Now let us see an application. What? All of you know that the small bits of papers are attracted by a plastic comb rubbed with dry air. Let us try to analyze the case on the basis of when dipoles are placed in non-uniform electric field. Okay, I am again saying small bits of paper. Example: small bits of papers are by a plastic comb rubbed with dry hairs. Okay, let us see this. How can we explain? First of all, the plastic comb, when rubbed with dry hairs, plastic combs, these plastic combs, let us say by 1. So that in the symbol, let us have a symbol illustrate. Just I am showing this. So let this plastic comb, actually when this plastic comb is rubbed with dry hair, then the plastic comb acquires negative charge. Okay? So first one is, when the plastic comb is rubbed with dry hair, then the plastic comb acquires negative charges. Okay? Then, let the small bits of paper small bits of paper, good small size of paper. Now the question is, because of this external electric field, these bits of paper acquires dipole moment, and here, though it is electrically neutral, but net negative charge is now developed right here, and this is the net positive charge. Induction. This is by induction. Recall induction. So the bits of paper induces positive charge near the core and negative charge at the far side of the core. So what is the result? This develops a dipole. Check this. This develops a dipole moment. And as dipole moment here, now what is the direction of the electric? Whatever it may be, parallel or anti-parallel, whatever you understand this. Here the direction of electric field. Electric field here in which direction? This is the direction of the direction of electric field and increasing. Increasing left-ward. A negative charge. So this is very common. As we move far and far away from the source charge, the electric field decreases. So negative charge, direction of electric field towards the charge, as is shown by this. This is the direction of electric field, and increasing to the left. Okay. So this is the direction of electric field, and this is the direction of dipole moment. So what is the direction between P and E? What is the direction between P and E? P is parallel to E. Check the first case. P is parallel to E. So if P is parallel to E, then in which side the dipole experiences a net force? Along increasing E. Since P is parallel to E, it experiences a net force along increasing. You check the first case, it is there. P is parallel to E, then the dipole experiences a net force along increasing E. Okay? And that is, what is the result? Attraction. So attraction. So net force. So along these directions. The dipole, I mean the small bits of paper, net force. Small bits of paper experiences a net force along increasing E, means towards the core, hence is attracted. Okay? It is this part. Now the next topic is Dipole. So this is what about when electric dipoles are placed in external electric field. Now the next topic. Next topic is work done in rotating the dipole in a uniform electric field. Okay. Work done in rotating a dipole in a uniform electric field. First, you have to think about that work done here by is not mentioned. Unless work done by is mentioned, it is difficult to calculate the work done. Simply what is the work done is not very clear, because we know work done can be the measures of positive and can be the measures of negative amount. So by the same force. So here work done in rotating, that means it is by external agent. So this is the middle. So work done by external agent in rotating a dipole in a uniform electric field. This is the matter. Okay? Now try to get the result. So let us consider the uniform electric field. And this is E. The direction of E, I have taken a single electric field length. Actually, as for the case, it is the uniform electric field rightwards. Okay? Then an electric dipole. Let this is minus Q and this is plus Q. So this is the dipole moment P theta with the electric field. Okay. Then what is the torque? Here check that work done by external agent. Here work is done not by force, work is done by torque, because turning effect is found in rotating. So work done in rotating, that means actually work done by external agent, and that work is done by torque. So first, what is the torque acting on the dipole at this orientation? At this orientation, how much torque is acting? Torque acting on the dipole equals tau E sin theta. P E sin theta. Torque acting on the dipole is P E sin theta. This torque is produced by electric field. It is by electric field. This is by E. So, to give a support, to counterbalance this torque, you have to give a support. You have to provide a torque in the opposite direction exactly by the same amount. So, the external torque external at this orientation is also equals P E sin theta. You check this. If we remove this external torque, then the dipole gets aligned with the field. But I am saying the orientation is this, making an angle theta. Unless you apply this much torque, the dipole can't be at this orientation. If you remove this external torque, then it will get aligned with them. So at this orientation, the external agent applies a torque P E sin theta to make it stable. Okay? To keep it, to hold it at this orientation. Now the question is, you know that as we rotate it more and more, then more and more external agent has to apply torque. So torque is changing. So the question is work done by variable torque. So what is the sequence? How to calculate work done by variable force? Similarly, work done by variable torque. So work done in rotating the dipole by d theta, how much? dw equals P E sin theta d theta. So the work done in further rotating by elementary angle d theta is how much? P E sin theta d theta. Okay? Tau d theta. As there you say f dx, here you say torque tau d theta. So P E sin theta d theta. Now our case required. So work done in rotating the dipole, from theta 1 to theta 2. That is W equals integration of theta 1 to theta 2 P E sin theta d. Okay? The elementary work is P E sin theta d theta. So total work done from initial orientation theta 1 to final orientation theta 2. You understand? Theta 1 and theta 2, the angle made by the dipole movement to the electric field. Then how much? P E sin theta d. Okay? So this will be, you do this. So this is how much? W equals minus P E cos theta 1 to theta 2. Integration sin theta d theta is result. Okay, minus P cos theta 2 minus cos theta 1. Understand? Purposely I have not operated minus with the bracket. I have kept the minus as it is. We shall learn the utility of this minus sign keeping outside bracket while we study the potential energy of the diagram. Okay? Now let us check this in some examples. So try to understand with the help of figure. The result, try to understand with the help of figure. So what I say, we check this in a small figure, try to remind this later. So I am saying this is E and this is P, this is making an angle theta. Okay? So this is the first step. Now we need, now the question is, we need, suppose this is E and the dipole making an angle theta 1 initially and then finally we change the orientation to theta. Then the question is, this is how much? Of course, what external? External. So this is the question. Initially, the dipole is oriented in such a way that the dipole moment makes an angle theta 1 with field. Now we need to rotate the dipole from this configuration to this configuration till the dipole moment makes an angle theta 2 with E. Then how much work is required to do by the external agent? It is this, exactly this. E cos theta minus P cos theta 2 minus cos theta 1. But students, if you operate this minus, you will have no objections. You can write easily P cos theta 1 minus cos theta 2. Easily you can write P cos theta 1 minus cos theta 2. No problem is there. They are same. But as I said before that, we shall use the statement again in finding the potential energy of the diagram. Okay? Let us take an example. It's very common numerical. I am saying this is very, very important topic taught and work done in rotating dipole and potential energy. Of these three parts, three topics, you can expect 5 marks or more even in the board. Let us take a numerical examples. The question language can be stated, but let us try to understand the language in figures. This is electric field, and here initially the dipole is making an angle of 60 degree, and you need to rotate it by okay, to this. Then the question is, what external is how much? So initially a dipole in such a way that dipole moment makes an angle 60 degree with the electric field. The question is, how much work is required to do in rotating the dipole to an angle such that the dipole moment makes an angle 180 degree with E. 180 degree with E. Okay, so just put the value here. So here simple value, simple. Here theta 1 is 60 degree, theta 2 is 180 degree, and therefore you do the question, what external equals minus PE minus PE. So cos theta 2 cos 180 degree minus cos 60 degree. Check the formula. Minus minus cos theta 1. Okay, minus PE cos theta 2 minus cos theta 1. So minus PE, then cos 180. How much? Cos 180. Say cos 180. Cos 90, cos 0 is 1. The cos 180 is cos 180 is how much? Minus 1. And cos 60 is minus half. Okay? Cos 60 is half. So this is PE 3 by 2. That is 1.5 PE. So on the minus gets plus, and then 1 plus half. So this is 1.5 PE. Check that this is greater than 0, and obviously you need to do greater one, positive one. See, this is the dipole. Let this is negative charge and this is positive charge. Let this is negative, this is positive. So this, and I am rotating this. Check this. Against electric field, against the torque produced by electric. So that must come positive. And I will rotate in this direction, then work done by external agent would be negative, because in favor of negative. Work done by external agent would be negative, and work done by electrical field will be positive. If this is a negative one, if this is negative charge, this is positive, and this is like dipole, oriented this way. If I try to rotate in this way, I am doing positive one, because against electric field. Electric field is doing negative one. I am doing positive one. But from this orientation, if I rotate in this way, I am doing negative one. But electrical field is doing positive one. Okay? So you must try more questions basis on this topic which are given.